Hi everyone. Today we are going to discuss about the physical significance of divergence. In the previous videos we already discussed about the vector integrals and vector derivatives. We already discussed about the physical significance of gradient. So in this video let's see what is happening to the divergence. So how we can prove that its physical significance. Okay. Let's start with the what is divergence. Let's see, we know that the divergence, which is the dot product of a vector function with a vector differential operator, and you're familiar with the vector differential operator as well as a wave function, a vector function. Suppose we have a vector function f of x, y, z, let its vector representation is fxi plus fij plus fzk, and the del operator is I into dou by dou x plus j into dou by dou y plus k into dou by dou z. These things are you familiar. So we know that our divergence is the dot product of the vector function with the vector differential operator, that is del dot f. And we know that in vector calculus, suppose we have two vectors, one is a and the other one is b. Suppose we are taking a vector dot product a dot b, the output will be a scalar output. Okay, similarly here also the divergence of a vector function, since it's a dot product of the vector function with the divergence, that is a vector differential operator, the output will be a scalar one. Okay, that is output is represented as dou fx by dou x plus dou fy by dou y. That is the partial derivative of that function with respect to x, y and z. Okay, so you can see here this is a scalar output, and the meaning of the divergence is the net outward flow, the flux. Okay, we can calculate flux by or we can understand the idea of a magnetic flux or an electric flux by knowing the value of the divergence of the electric field as well as magnetic field. Okay, so in this video what we are going to do is we are going to prove the physical significance, the net outward flow of liquid, field or whatever is representing the divergence. That's what we are going to do in this video. Okay, let's begin in the class. Let's see the physical significance. I'm representing a figure. This is a parallelepiped. Okay, in this parallelepiped, and it is a rectangular parallelepiped, and P is the middle of the parallelepiped. Okay, the P of x, y, z be a point at the center of a small rectangular parallelepiped. The sides of that particular parallelepiped is delta x, delta y and delta z. And I'm representing something, some fluid is flowing through the parallelepiped. So this arrow, red color arrow mark, which is representing the fluid flow, and some kind of fluid is flowing through the parallelepiped, and this is flowing out. So this is the inflow and this is the outflow. And I want you to know that when a fluid is entering into this, it is a negative value. When a fluid is leaving, it is a positive value. Okay, so I have represented the velocity of the fluid as v of xyz. So in vector form we can say that v of xyz is equal to what? Vxi plus Vyj plus Vzk. That is the Vx, Vy and Vz are the component of the velocity along I, J and K direction, right? So that is here. So the component of the velocity along x-axis is Vx. The component of the velocity along y-axis is Vy and z-axis is Vz. Okay, that is the components of the velocity. So here what we are going to calculate is, initially I am starting with the x-axis. Okay, so I have represented y here, z here and x here. So I am representing the fluid flow along x-axis. Then I will be approximating it with the y-axis and z-axis. Okay, so Vx is the initial, that is the component of the velocity along x-axis is Vx. So let's see, I have represented a rectangular face here, that is A, B, H, G. So let's see what is the component of the velocity along this particular area. So we know that the initial velocity was Vx, and since the fluid is flowing in, so there will be a minus thing. So there will be something happening to the fluid when it is traveling along this x direction. Okay, so something happening to this fluid while traveling along the x direction, and the distance I told you, this is at the middle of the parallelepiped. So if the sides are delta x, delta y, delta z, so this particular point can be approximated to delta x by 2, delta y by 2 and delta z by 2. Okay, so I want you to know that the fluid is flowing along the x-axis, and we are going to check what is the net flow along the x-axis. For that I have a face ABHG. So let's see what is the component of the velocity at the center of the ABHG. So the velocity at the center of the ABHG is Vx, that is the x component of the velocity, minus dou Vx by dou x, that is the change in the velocity with respect to the x-axis into the distance delta x by 2, because this is at the center of the ABHG. Okay, so the velocity of the fluid at the center of the face ABHG is Vx minus dou Vx by dou x into delta x by 2. This minus is because it is coming in. If it is flowing out, it will be a plus quantity. So the volume is what? We have delta x here, that is the distance. So the volume of this particular fluid at the center of the ABHG will be what? The volume will be equal to Vx minus dou Vx by dou x delta x by 2, that is the velocity, into delta y delta z. Okay. So the volume of the fluid entering through ABHG will be this thing. Similarly, consider the component of the velocity along this ECDF, that is fluid is flowing out. So the component of the velocity will be Vx plus dou Vx by dou x into delta x by 2. Since the fluid is flowing out, the sign is positive. Then the volume will be what? The volume will be the velocity into delta y into delta z. Then the net outward flow, what will be the net outward flow? The outgoing flux minus the incoming flux. Okay, that is the volume flowing out, that is ECDF, minus the volume flowing in, that is ABHG. By subtracting that, we got the velocity or the net outward flow along x-axis is dou Vx by dou x into delta x, delta y, delta z. Similarly, in the y-axis, we will get the net outward flow will be dou Vy by dou z. To calculate the y-axis, you can see this is the y-axis. Okay, this is the y-axis. So what you can do? You can do is you can take the two faces along the y-axis and you can equate. Okay. Similarly, along z-axis also you can see, you can take two faces along z-axis and you can see the inflow and outflow. So the volume, the net outward flow along the y-axis is dou Vy by dou v. That is the change of the velocity with respect to y-axis into delta x, delta y, delta z, and similarly along z-axis is dou Vz by dou z, delta x, delta y, delta z. So we got the net outward flow along x-axis, along y-axis and along z-axis. So we can summarize that the total flow along the three axes together, the total flow will be what? The total flow will be that dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z, since this is a common thing, right? Delta x, delta y into delta z. That is the total flow. Then what is the net outward flow per unit volume? Okay, so we can divide it with the delta x, delta y, delta z, since it is representing the volume. So we will get the net outward flow is the derivative or the change in Vx with respect to x plus the change in Vy with respect to y plus the change in Vz with respect to z. What is that? That quantity is representing the divergence. So the divergence of a vector function, whatever the fluid flow or the field or whatever it is representing the net outward flow through unit volume. Okay, so the divergence of a vector function at a point is a net, it is representing the net outward flow per unit time at that point. Okay, that is the physical significance of divergence. To understand that, this you want to think about the picture. We have a parallelepiped, we have a particular point P at the right, the middle of the parallelepiped. To evaluate each component, first we took two faces which is along the x-axis. We calculated the inflow and we calculated the outflow velocity. Then we find the volume and we calculated the net flow along the x-axis. So we got a particular value. Similarly for y-axis and z-axis we got the net flow. So as a whole, the net outward flow is the along these three axes is calculated. Then we took the unit volume, that is divided by the volume. We got the net outward flow, which is equivalent to the divergence of that particular vector function. Okay, per unit time at that particular point. I hope you understood the concept of this physical significance, and I want you to make notes, because just listening to the class is not enough, because you will definitely forget. These things are required for coming derivations. Okay, so I want you to understand the class. If you have any doubt, you can ask me, and or you can text me, and I can definitely help you to understand the topic. Okay, thank you.